This Arduino transmits data with nothing but a ferrite antenna connected to it. How is this possible? Does it have a secret transmitting unit? Spoiler alert, yes it does. In this video we will find out how to use it. Stick around. Well, the secret transmitter is actually the Arduino's internal hardware timers, which can generate frequencies of up to 8 MHz. With an appropriate antenna and amplifier, these can theoretically be transmitted worldwide. I have already made a video on how to transmit music on the AM band using an Arduino. I also dig into the details there, so check it out. But nowadays, digital data transmission has become even more important. There are many ways to modulate bits and bytes, the simplest being ASK or Amplitude Shift keying. ASK works by turning the carrier on and off to match the bits of a serial bit stream. We can easily get this from the UART on the Arduino. To generate the carrier, we use the 8-bit timer number 2. This is configured to increment every 125 nanoseconds. When it reaches a constant in the two compare registers, the levels on the output pins toggle alternately. This way we can get a variety of possible frequencies to output on pins 3 and 11. Since these pins toggle alternately, we can connect the ferrite antenna directly between them and get an alternating current through its coil. And with the right capacitance in series, the antenna will resonate for the best efficiency. By trial and error, I found that 33 and 3.3 picofarads in parallel work best there. Now let's look at the code. Timer 2 is initialized in the setup function. And there the compare registers are initialized with the value that determines the output frequency. The possible values are defined at the top of the source code. The bit stream to be modulated comes out of the DX pin and is fed into pin 2, where it fires an interrupt on each change. When the interrupt service routine is called, it switches RF pins 3 and 11 either as input or output, depending on the actual level on pin 2. This means that when the pin is low, the RF signal is turned on, and when it is high, the RF signal is turned off. In the UART protocol, high level means idle, but we don't want the Arduino to transmit when there is no data to send. So 1 means off and 0 means on. By the way, we will send the standard frame format with 8 data bits, 1 stop bit and no parity. As soon as we initialize the unit with serial begin, the Arduino is ready. To start the transmission, we can simply call the familiar serial print function. For the test, I will send a string into which I have inserted some values that count up every second. Now let's look at the receiver side. It's not so easy there, because we need some additional components. The Arduino can send, but not receive by itself. So it needs some kind of a receiver. There it is. The tiny little thing that looks like a transistor is actually an AM receiver IC. Fortunately, it requires few external components and provides us with our demodulated serial signal. An op-amp compares it to a threshold, which we can adjust with a trim pot. At its output we get a clean TTL signal, which is finally fed directly into the AX pin of the Arduino. The Arduino's cache simply reads the received text from the buffer and displays it on an LC display. Now let's fire it up. It runs on a lithium battery followed by a boost converter. This will come in handy later when I test its range. I place the transmitter next to it. With an oscilloscope attached, I tune it to its 1600 kHz. I configured the transmitter to continuously transmit uppercase U's, which is 55 in hex, resulting in a continuous 1200 Hz square wave. This makes it easy to tune it to the maximum. Again, I configured the transmitter to send some text. Now I adjust the threshold of the comparator to get our clean waveform for the Arduino RX pin. Et voila! The data sent and received by an Arduino. If you like what you see, hit that like button. Also check out the other videos on my channel. Subscribe and click the notification bell so you will always be notified if there's a new video. Thank you to all my supporters on Patreon. And I'd like to thank the sponsor of this video, PCBWay. Not only they have provided me with high quality PCBs that are fun to assemble, they also made the 3D prints for my laser scanning microscope that I made out of a Blu-ray player. The parts are robust and fit together seamlessly. And since I don't have a metalwork workshop, they also made a beautiful brass cover for my all-in-one meter. See how nicely it fits the VFD tubes and holds them in place. And of course you can order all of their services on their website. So all that remains is to say, PCBWay is the right partner for all of your projects. Check it out. I'm gonna test its range now. I mounted the receiver on a tripod at a distance of 150 centimeters from the transmitter. It gets a new value every 500 milliseconds. Now I increase the distance to the receiver. About 6 feet away, things start to get messy. I'm trying to fix this by adjusting the threshold of the comparator. And here we are again. Now we have reached the end of the ruler. Let's give it another shot. And I still managed to get it in. Let's pull it another foot. Okay, it still receives, but with errors. No matter how hard I try, it's not getting any better than this. So we can summarize that the maximum range is about 2 meters or less than 7 feet. The next interesting question might be about the maximum baud rate. I did the previous test with 2400. Up to 9600 works fine, but with reduced range. Here it's running at 19200. It's still possible, but with a lot of errors. Let's say that sending data with an Arduino is feasible if you only need to send across your workbench and only need low speed. For all other applications you might want to use a pre-built 433 MHz RF module.